Hi, hello, good morning everyone. How are you all? Hope you are doing good. Uh, so, I'm missing you all so much, and also I miss our college and classroom as well. I hope you also missing your college, your classrooms, and your teachers. Apart from that, we will soon meet on April 15th at our department. So, I'm very much excited and very much waiting for that day. Okay, now again, this is your coordinator, Srimati Pratibha Kanvi. So, I welcome you for PG Physics Nuclear Specialization class. So, this is the fourth class I am conducting, and we discussed beta decay process in the earlier class. So, where we have stopped, this is the first question I regularly ask in the classroom. I think you don't remember. You don't forget this one. Okay, leptonic number conservation of beta decay process we discussed, right? Beta positive decay, negative decay, and electron capture process. So how the neutrino and antineutrino particle are being generated during the beta decay process, that also we have discussed. So now let us discuss today's topic is very important, that is Fermi's theories of allowed beta decay transition. So let me open that file. uh, sorry. Okay, we'll start at this point. Fermi theory of allowed beta decay. So please take a notebook and pen and write down the equations, whatever the equations we arrive during the lecture. Please note down the equations, because so I'm having that the Android phone, but I'm not sure that so how much it cooperates, that so to use the screen it is not cooperating. So that's why I'm doing the pronunciation only, and you have to write down the equations. Okay, so I think my students are very I know, so my students are very cooperative and friendly. So now Enrico Fermi developed a theory of for allowed beta negative decay based on Pauli's neutrino hypothesis. Pauli neutrino hypothesis we discussed in earlier class. So Fermi used the result of Dirac's time dependent perturbation theory, so which you learnt in quantum mechanics, perturbation theory approach, according to which the rate of transition from an initial state to a final state F is given by C. So you can take this as equation number 1. W is equals to 2 pi by h cross and matrix element hij square into rho of E, where hij is the matrix element of the perturbing interaction. Perturbation is nothing but what? Disturbance of the particle in the system. So h causing the transition and is given by. So where hij can be written as, so that is transition from initial state to final state. Okay, so rho of E is the density of the final states. So equation 1, so 5.71 they have written. You can put this is equation number 1 and this is equation number 2. So equation number 1 can be applied to the case of emission of electromagnetic radiation from the atomic system. An excited atom in an initial state makes a radiative transition to the ground state, which consists of the atom in the ground state plus the emitted photon. So transition takes place, again the photon will be emitted, and atom which is comes from the higher state to lower state. So according to Fermi, the beta emitting nucleus makes a transition such that the final state of the product nucleus plus the emitted electron and the neutrino. The initial state is of course parent nucleus. The transition can be written as, so you can put this is equation number 3, x of a z, which is converted to y of a z plus or minus 1, whether it may be beta positive decay or beta negative decay, plus the liberation of electron and neutrino or antineutrino and positron. So where is where E is either the electron or the positron, while V is either an antineutrino or a neutrino, since the emission of a particle is equivalent to the absorption of an antiparticle. So we represent the beta transformation process by the following equation. By using this equation number 3, again we can write like this. Okay. As we have seen, during beta negative transformation, a neutron in the nucleus is transformed into a proton with the creation of an electron and antineutrino pair, while the beta positive transformation, proton in the nucleus is transformed into a neutron with the creation of positron and neutrino pair. So now using this equation number 4, this is see, this is equation number 4. Okay, this is equation number 4. We thus see that the initial state of a function psi I in equation number 2, this is equation number 2, that is matrix element, um, should consist of the initial state nuclear wave function ui and the leptonic wave function pi v, while the final wave function psi f should consist of the final state nuclear wave function uf and the leptonic function pi b. Okay, because pi b indicates that is pi b is for leptonic wave function for beta and leptonic wave function for neutrino. Okay. In the case of radiative transition, the perturbation causing the transition is the electromagnetic field, whose quantum manifestation is the photon. Its form is noun. However, in the case of beta emission, the nature of the perturbation is not noun. It may be called the electron neutrino field. Getting my point? In the case of radiative transition, the perturbation causing the transition is the electromagnetic field, whose quantum manifestation is the photon, that is intermediary is photon. It is noun. But however, in the case of beta emission, the nature of the perturbation is not known. It may be called the electron neutrino field. Its quantum manifestation is a pair of these two particles. The electron neutrino field interacts weakly with the nucleus undergoing beta transformation and is known as the weak interaction field. This follows from the fact that the mean lifetime of beta decay takes up to minimum 10 raised to minus 3 seconds, which are long compared to the characteristic nuclear time, which is the time taken to the nucleon to travel across the nucleus, that is 10 raised to minus 23 seconds. But for the beta decay process, it takes time 10 raised to minus 3 seconds. This is the long duration compared to nuclear characteristic time. So beta decay theory is best beset with another difficulty. The exact forms of the nuclear wave function are not known. Fermi chose the simplest form of the electron neutrino field, which was relativistic invariant. The relativistic form of the theory must be chosen because the electron and the neutrino both move at relativistic velocities. The matrix element can be written as see, again write this Hij is equals to equation, and please keep the equations. I don't remember, so you should be followed. You should follow my instructions and guidelines to note down the equations as I told you. So here f of Rn is a quantity which depends on the wave functions, that is pi b and pi v of the emitted electron and neutrino. So pi b is the leptonic wave function for emitted electron, pi v is the leptonic wave function for neutrino at the position of the nth nucleon undergoing beta transformation. Okay, so up to we'll move the page. You can refer the page number 116 in S.N. Ghoshal book. So we will move with page number 117. Wait for a while. Okay. So it is be a bilinear combination of the wave function, that is pi b and pi v of the electron and neutrino. On is an operator connected with the beta decay of the nth nucleon. Taking the simplest form in which the transformation of only one nucleon is involved, we then write. So again write that equation, previous equation, just modification they have done. G is a constant, where G is a constant whose value determines the strength of the interaction. So whether the interaction is weak, strong or electromagnetic, that can be determined. It plays the same role as the electronic charge E in the case of radiative transition. We assume that all the particles interact at a point. The interaction operator O can have one or more of the 5 specific forms known as the scalar operator, polar vector operator, antisymmetric tensor, axial vector and pseudoscalar. Okay, up to this scalar. So we shall go into more details later in discussion. So I don't think so this is not more useful to you. So but please do remember for the Fermi theory of allowed beta decay. For the electron and neutrino wave functions, we consider plane waveforms normalized within a volume omega. So again the leptonic wave function for electron and leptonic wave function for neutrino. leptonic wave function for electron and leptonic wave function for neutrino, which are emitted during the beta decay process. That can be represented by 1 divided by root of omega exponential of I into kb into rb. This is I into kb into rb, where k's are the wave vectors through the plane waveform. For pi v is justified. For pi v is justified, that for pi b is not, except for low z, since there is a Coulomb interaction between the beta and the nuclear charge. However, as we shall see, presently to a first order of approximation, it does not make any difference if we neglect the Coulomb effect. For high Z nuclei, however, the effect must be taken into consideration. See here, for the low Z elements, the Coulomb interaction between the beta and the nuclear charge, however, we shall see presently to a first order of approximation. It does not make any difference. We will not see that kind of difference. That should be neglected. Coulomb interaction should be neglected for low Z elements. And for the high Z nuclei, however, the effect must be taken into consideration. For the energies involved in a beta decay, the electron or the neutrino momentum is given by Cp is equals to E by C. E is equals to, in terms of MeV, 1.6 into 10 raised to minus 13 divided by 3 into 10 raised to 8. And also they have evaluated lambda cross K. So for a nucleus of radius R is nearly 5 into 10 raised to minus 15 meter, we get Kr is equals to 0.025, which is very less than 1. Since the integration in the calculation of the matrix element has to be carried out within the nuclear volume, we shall be justified in expounding the expression for pi b and pi b in Taylor series and neglect all terms other than first. So leptonic wave function for pi b, 1 by root omega plus, so expanding the terms by using Taylor series, 1 plus x square by 2 factorial plus x cube by 3 factorial, like that, where x is equals to I into kb into rb. So that gives 1 divided by root of omega. Similarly, the leptonic wave function for neutrino is also gives the same response, that is 1 divided by root of omega. Okay. So now you can refer the page number 117 for Fermi theory of allowed beta decay transition. Again we go to the next slide. Wait for a minute, sorry, while 44. Okay, here these approximations correspond to allowed transitions. Then the initial and final state wave functions can be written as psi I is equals to ui into pi v. Pi v is equals to 1 by root omega. Again psi f is equals to uf into pi b. Uf, again pi b is equals to 1 divided by root omega. So then the matrix element then becomes, you can refer the equation number 2. So in initial I have told you to write down the equations. Okay, you just write down the equations. So it which gives the matrix element which gives g divided by omega into MIF, where MIF can be written as like this, where MIF is the nuclear part of the matrix element excluding the strength factor G and the normalization volume omega. So now calculation of the density of states. Calculation of the density of states. The number of states of the neutrino in the momentum range PV to P plus dP when it is anywhere within the spatial volume omega is given by the number of states of the neutrino dn is equals to 4 pi p square into dpv omega divided by h cube. Similarly, for the electrons, the number of states in the momentum interval pb to p plus dpb is again same for the neutrino and for the electrons. This is the total number of states available for the beta and neutrino in the above momentum ranges when they are confined within the volume omega can be written as dn is equals to dnb. dnb is nothing but total number of states available for the electron and available for the neutrino. So after the calculation, finally they will get 16 pi square omega square divided by 2 pi h cross raised to 6 pb square pv square dpb into dpb. Okay, and to get the density of states, we have to divide dn by the energy interval deb for the electrons to get the density of states. Dn by deb, but since eb plus ev is equals to m, where m is a constant, hence deb plus dev, differentiation of this is equals to 0. Since EV is equals to C into PV. In terms of momentum, EM minus EB, we have DEB is equals to minus DEV by using this equation. DEB is equals to minus DEV. DEV is nothing but minus C into DPV. Okay. So then density of states is equals to, so you can see dN by dEB. dN you know this much, so put this value here, and dEB is nothing but minus C into dPV. So at final expression we get, substituting for PV, we get finally, that is omega square divided by 4 pi raised to 4 h cross raised to 6 c cube PB square into bracket EM minus EB whole square into dPB. Okay. So up to this clear, that is calculation of density of states. So we'll again move with another slide. 55, 46. Okay. So by using previous equations, we get from the probability of emission per second of the beta particles in the momentum range PB to PP plus dPB as see here. So this is what the probability of emission per second of the beta particles in the momentum range PB to PB plus dPB. That is again substituting the values, that's it. So by referring the previous equation, you sort it out the expressions. If any queries found, you note it down, cite by your notes, and ask me later. So you can call me and you can message me, or else so you just note down all the queries or doubts. You can write down and you will make a list of it. We will discuss when we meet at a college. Okay, this expression is independent of omega. See here, in this expression we cannot see the omega parameter here, hence this expression is independent of omega, that is nuclear volume. Hence this equation gives a Fermi distribution for the emitted beta particles in allowed beta decay. So this expression gives the Fermi distribution of the emitted beta particles in allowed beta decay process. Okay, so please make a note on Fermi theory of allowed beta decay. This is very, very important up to the equation number 5.721, from 5.71 to 5.721. So make a notes and write down the doubts and read it out. So again we will be back so with the another topic, that is Coulomb corrections. So we'll discuss it later, Coulomb corrections for the Fermi theory of allowed beta decay. So hope you guys you are getting what I am explaining. So I don't think so that much expectation it would reach or not, but I'm trying my level best to approach you. So please cooperate with me. Again I will be back with you at evening. Bye everyone.